Good morning, everyone. A very warm welcome to the Citizen Science Workshop being organized by the Blue Carbon Lab of Deakin University in collaboration with the James Michel Foundation. For those of you who don't know me, I'm Mahe, one of the Blue Carbon team members driving this project in Seychelles. So this workshop is part of a SeyCCAT funded project titled The Roadmap to Blue Carbon Opportunities in the Seychelles, which began in October 2019. The project aims to advance Seychelles' blue economy by exploring blue carbon opportunities in the region and developing a better understanding of marine assets that directly mitigate climate change and reduce ocean risks. So far, the core deliverables of this project have been as follows. So we delivered a literature review that was based on research of the tropical Western Indian Ocean, and it was published in March 2021. Secondly, we initiated a stakeholder questionnaire, which was completed and compiled from over 100 individuals and organizations locally in Seychelles. Many of you in this room today played a part in that process, and so we thank you all for your participation. We are now in the final stages of the project, and this includes this workshop today, and we'll aim to introduce you into the world of blue carbon ecosystems and demonstrate field monitoring techniques that are used to collect blue carbon data. The final deliverable of this project will be the roadmap document, which will be submitted to the government of Seychelles at the end. Okay, before getting into the workshop, just a bit of housekeeping announcements. As we are all aware, COVID-19 still poses quite a big risk to our community, so we ask everyone to wear their mask at all times, except obviously if you're asking a question or you need to speak into the microphone, then you can remove your mask. So thank you very much. I really hope you enjoy today's workshop. I'm just going to go onto my computer now. Okay, so I'm now going to just share a video from former President James Michel, as well as Professor Peter McGreedy at Deakin University.
Ladies and gentlemen, it is my great pleasure to welcome you to this Blue Carbon Ecosystems and Monitoring Techniques workshop by the James Michel Foundation and Blue Carbon Lab of Deakin University in Australia. This workshop is part of the Blue Carbon Project, which is being supported by a grant from the Seychelles Conservation and Climate Adaptation Trust. The coastal areas of Seychelles' inner and outer islands are home to 8 species of mangroves covering 1.7 million hectares and 2 million hectares of seagrass ecosystems. A short walk around this workshop venue and its surrounding areas will give you a glimpse into the vastness of these intricate ecosystems. Despite being quite small in terms of global proportions, their roles are pivotal in fighting climate change and in conservation. Both offer shelter, protection, food, and breeding grounds to a wealth of biodiversity. They also support livelihood and offer services to the communities, as well as accretion and preventing erosion. Till very recently, these habitats were poorly understood and sometimes taken for granted, even sacrificed to make way for infrastructure development. I am sure you know this better than I do, so I will not dwell on them today. I will instead focus on their importance as carbon sinks in the context of the blue economy and climate change, which are my subjects of passion. The development of the blue economy is dependent on healthy marine and terrestrial ecosystems, which in turn supports economic activities. The blue economy is about sustainability. There cannot be a sustainable blue economy without conservation and protection. Seychelles has been at the forefront of environmental protection for many years. It is our way of life. We are doing what we can towards the bigger global effort to heal and protect our oceans and coastal areas. Dedicating 30% of marine space as protected areas is testimony of the importance that Seychelles places on biodiversity protection. Seychelles has further committed to protect at least 50% of its seagrass and mangrove ecosystems by 2025 and 100% by 2030, which of course will be with external support. This is remarkable progress in the fight against climate change, and it underlines the importance of these ecosystems as nature-based solutions. The Seychelles Islands, like other small island developing states, or rather, big ocean states, are bearing the brunt of the effects of climate change. Stretches of pristine coasts are left vulnerable to erosion and coastal communities to flooding. Increased adverse weather events are negatively impacting fisheries, tourism, and other ocean-related businesses, which severely affect livelihoods. Ladies and gentlemen, mitigating climate change is very costly, as it also requires technology transfer and importing knowledge from abroad. But part of the solution lies in nature itself. The scientific community tells us that seagrass meadows and mangrove forests can trap carbon 30 to 50 times faster than terrestrial forest, and that 80% of the carbon is stored in the soil, where it is locked away for centuries to millennia. They both absorb huge amounts of carbon dioxide for photosynthesis and release oxygen into the atmosphere. In so doing, they contribute to reducing greenhouse gases, thus global warming. It therefore makes ecological and economic sense to ensure their protection against negative human interferences. Considering all this, my foundation, along with the Blue Carbon Lab of Deakin University in Australia, initiated the present study which explores the Seychelles blue carbon future by developing a first-pass assessment of potential blue carbon opportunities in the Seychelles and building local capacity and literacy on blue carbon. It aims to account for the ocean's carbon offsetting capacity, which can help Seychelles become a net carbon sink and achieve its nationally determined contributions. Moreover, many of the costs of achieving emission reductions in the energy and transport sectors could be met through international climate financing and blue carbon markets. Ladies and gentlemen, I sincerely hope that the various presentations will be very informative and insightful to you, and that the field of demonstration and data collection activity will be enriching. I am grateful to the scientists presenting today and others who are working on this important project for Seychelles. I wish you a fruitful workshop and look forward to reading the workshop report later. I thank you.
On behalf of Deakin University's Blue Carbon Lab and in partnership with SeyCCAT and the James Michel Foundation, it is my pleasure to welcome you to this Blue Carbon workshop. Blue carbon is such an exciting area right now. It's one of those great news stories in the fight against climate change. Blue carbon ecosystems store more than 30 billion tonnes of carbon across 185 million hectares. And if we stop destroying these ecosystems and we restore them at scale, we could achieve over 1 billion tonnes of CO2 abatement each year. That's equivalent to 3% of global carbon emissions, or more than 2,200 times that of the Seychelles annual carbon emissions. As you might have noticed, there's no shortage of demand from government and the private sector for blue carbon projects for the sake of offsets, but more generally because we know these ecosystems are critical for lives and livelihoods. Our challenge is to establish blue carbon as a natural climate solution. And for many countries, this means operationalizing blue carbon markets. We really hope that the Seychelles can capitalize on blue carbon opportunities. So here's how today is going to go. We will start by introducing you to fundamental concepts about blue carbon. What is it? Where is it? Why is it important? Then we are going to look specifically at blue carbon in the Seychelles. The team have been busy collecting and analysing data, and you are going to hear some of the discoveries. What is the scale of opportunity? Where to act? A lot of this information hasn't even been released to the public yet. You are the first to hear about our findings. Then there will be some question and answer time, and then we are going to take you out into real blue carbon ecosystems so that you can get your feet wet and muddy and practice blue carbon sampling techniques. We really hope that today's workshop will help improve your understanding of blue carbon, and most importantly, we hope that it will empower you to learn more and start taking action. I thank you for attending, and I'm sorry that some of our team cannot be with you in person. We are here with you live to answer any questions. International travel is starting to resume for Australians, and I hope that many of the Blue Carbon Lab team can come to join you in your amazing country and meet you face to face. Thank you.
Hi, I'm Maria Palacios, one scientist from Deakin University's Blue Carbon Lab, and I'm going to be the one kicking off today's talk, giving a bit of background and general context about blue carbon science. So wetlands are basically a territory of land and ecosystem that gets constantly flooded by water. Because we're going to be talking about coastal wetlands, this means these ecosystems get flooded usually by saline or brackish water. They can be flooded most of the time, such as it happens with seagrasses, but they can also be just flooded sporadically, like it happens with tidal marshes. But why are coastal wetlands so important? Why are they such a hot topic? Basically because they provide a lot of ecosystem services to people and nature. So for example, they enhance soil retention and coastal resilience. They support wildlife diversity. They support livelihoods from fisheries and tourism, and they also improve water quality. Last but not least, they also are amazing natural carbon sinks, and they're actually a really efficient natural climate solution. They can actually trap and store a lot of carbon dioxide from the atmosphere, helping us, of course, fight climate change. But how does this actually happen? So you might recall the process of biosequestration, which you probably learned back in science class, where photosynthetic organisms and plants basically just take a big breath in of carbon dioxide, and they use the carbon molecule to grow and to create their branches, their leaves, their stems, and then they release a bunch of oxygen back into the atmosphere. Now, whenever this process of biosequestration is happening in typical green forests, then we call those green carbon ecosystems, and we call that carbon that is getting trapped, we call it green carbon. Obviously, because oceans are blue, whenever marine or aquatic coastal plants are doing the process of biosequestration, then we call them blue carbon ecosystems. And we call blue carbon that carbon that is stored and captured by coastal and marine habitats. Now, the interesting thing is that most of the world's blue carbon is actually stored by 3 specific ecosystems. We have seagrass meadows and mangrove forests that tend to flourish mainly in the tropical regions, but we also have tidal marshes, which are very common and very important in more temperate areas. Now, the interesting thing is that these 3 blue carbon ecosystems occupy less than 1% of the seafloor. They're just like basically all around the continents, but they store more than 50% of all the ocean's carbon. Okay, so how can this happen? Why are these ecosystems so small in size, but so mighty? So basically, there's 2 main reasons. So the first one is because they have a really fast carbon burial rate. So this graph puts head-to-head blue carbon and green carbon ecosystems. And you can see how any of those blue carbon ecosystems can store almost 40 times faster carbon than any of the green counterparts. And the reason for this turns out that most green carbon ecosystems accumulate and store that carbon mainly just above ground. But blue carbon ecosystems can also store heaps of carbon below ground in the root system. Another reason why they accumulate so much carbon is because they're in a very particular strategic location between the land and sea. So this means they can accumulate, trap, and retain a lot of organic matter that just gets dragged and flushed there from ecosystems nearby. Right. So the second good reason is because they have long-term carbon storage. So basically what happens is that everything they put into the soil gets actually locked for millennial timescales. So it turns out that usually soils in wetlands, I'm sure you're going to get to see when you go to the field, are packed with waterlogged, really muddy soils that have really low concentrations of oxygen. Because of these conditions, bacteria are really, really limited at the speed and the rate at which they can decompose those carbon pools. So basically, all the organic matter and carbon that gets put in there gets trapped almost for millennial timescales. Now, let's talk a bit about the carbon pools and where all that carbon gets actually stored. So in blue carbon ecosystems, typically we have 2 different carbon pools. One is the plant carbon pool that includes all the carbon that is stored in the biomass. So we could have the above ground biomass, meaning all the carbon in the leaves, the branches, the stems, but we also have the below ground biomass. So that means all the carbon that is stored in the roots and the rhizomes and the underground layer. The second carbon pool is the soil carbon pool, which includes all the carbon that is kept and locked within the sediments underground. The important thing to know is that in general, blue carbon ecosystems, most of the carbon is actually stored underground in the soil. Usually the most important and significant carbon pool. It is also really important because that 70% of the carbon stored in the soil is actually the one that is going to be kept for centuries on millennial timescales. Because remember, that soil carbon pool is the one that has the perfect conditions and the really limited decomposition to allow carbon to be retained and maintained for centuries. It's actually the carbon in the soil carbon pool that usually gets accounted in carbon inventories. Blue carbon science only started about 10-15 years ago, and it's peaked in the last years. Research has largely been focused on figuring out how much blue carbon we have and what is really its potential to mitigate climate change. For example, we know that on average, a 1 hectare of mangrove forest stores around almost 400 tons of carbon, while 1 hectare of seagrass tends to store generally around 100 tons of carbon. Now, obviously, this changes a lot from ecosystem to ecosystem, but one general trend we've found is that tropical Ecosystems that have a mixed stand of species tend to accumulate the most carbon in the soil. We've also now realized that across all blue carbon ecosystems in the world, they are storing around 30,000 teragrams of carbon. And to put this into perspective, that is equivalent to the weight of around 3 million Eiffel Towers. Now, the problem is that only around 2% of those blue carbon ecosystems is actually protected within marine protected areas. And that means that a lot of them are getting lost at a really fast rate. Now, the problem of losing blue carbon ecosystems is not that we just prevent them from capturing more carbon. The big issue is that all the ancient carbon that has been stored there for centuries and millennia gets thrown back into the atmosphere. So, for example, this video is showing some of those greenhouse gases, specifically methane, getting back into the atmosphere, obviously making climate change even a bigger issue. As you can imagine, stopping and reversing the loss of blue carbon ecosystems is really important for climate change mitigation. In fact, we've estimated that protecting all the blue carbon ecosystems around the world would avoid the emissions of around 300 teragrams of carbon dioxide equivalents per year. And this is actually the potential of mitigating around 0.5% of the global carbon emissions. It is really important that, of course, we focus on preventing any direct degradation on coastal wetlands, such as coastal development or changes in land use. But it is also important that we keep an eye out for many more indirect and silent ways in which these ecosystems are actually getting degraded. For example, in a study here in Australia showed that it is also important to take care of the whole ecosystem and all the trophic interactions happening within. For example, we found that whenever top predatory sharks are removed from coastal waters, there's usually an explosion of sea turtles. And sea turtles are all nice and cute, but when you have hundreds of sea turtles grazing and overgrazing on all the seagrass meadows, then they disturb a lot those seagrass meadows that release all the carbon back into the ocean. Another example is that it is really important to manage all the coastal area in a cohesive manner. For example, we need to make sure that there's no runoff or no excessive nutrients getting to the coastal waters, because all the excessive nutrients, nitrogen, phosphorus, can change the magical chemistry of the soil, allowing microbes to be activated and start really degrading the carbon stocks. So it is really important that we protect our ecosystems in marine protected areas, but that we do it in a cohesive and ecosystem sort of way. Nowadays, the good thing is that we don't have to limit ourselves just to protecting these ecosystems. We can actually directly manage and restore them to enhance the amount of carbon that is getting trapped. Results from a recent study actually showed that if we decided to go big or large and do like full large-scale restoration and restore all the blue carbon ecosystems that are degraded around the world, we would be able to remove an additional 840 teragrams of carbon dioxide equivalents, which is basically equivalent to mitigating around 2.5% of the annual global carbon emissions. Restoration of blue carbon ecosystems usually requires different levels of intervention depending on how degraded the ecosystem is. The first step is usually to stop all sources of degradation, such as stop any logging or stop any pollutants that are being discharged in the area. If the ecosystem is not super destroyed, this is usually enough to allow it to naturally recover. However, if the ecosystem is really bad, then we need to take more active measures, such as fixing the natural tidal hydrology or directly planting vegetation to speed up the recovery of the site. In the last century, there's been a 10-fold increase in the number of blue carbon projects that are getting done. And one of the main things we've learned is that usually mangrove restoration seems to be the one most cost effective and the one that leads to the greatest carbon gains. Seagrass restoration has been quite tricky, and there's been only very few successful stories. At the moment, the good news is that at the moment, there's lots of research trying to improve and test new tools and techniques. So hopefully in the near future, we will be able to see more cost-effective and large-scale projects. As we've entered into the UN Decade of Ecosystem Restoration, we really do hope that nations take more seriously their commitments towards blue carbon ecosystems. The potential of them to offset around 30% of the global carbon emissions, while also providing a bunch of additional ecosystem services for coastal adaptation and local livelihoods, obviously justifies all the attention that blue carbon is receiving as a natural climate solution. Our current challenge is mainly to break through all the financial, governance, and social barriers to be able to enable a widespread implementation of blue carbon projects.
Hi everyone, welcome to the next part of the Blue Carbon Workshop. I'm Dr. Melissa Wortman, a research fellow in the Blue Carbon Lab. In this next presentation, I'm going to be taking you through some of the blue carbon method and techniques for collecting and analyzing data specifically from mangrove ecosystems. So I'd like to begin by directing your attention to a very valuable resource, which is the Blue Carbon Manual. And it's a step-by-step guide that takes you through assessing carbon stocks and emission factors in mangroves, salt marshes, and seagrass meadows. And it's freely available online. You can get it from the Blue Carbon Initiative website. And it goes into a lot more detail than what I'll be covering here today. You'll also have the opportunity after these workshops this morning to go out into the field and learn from Dr. Barry Norris, who is doing the mangrove sampling field assessment here. And so you'll get to learn from him and his team and get that hands-on experience. So ask lots of questions. Barry will gladly be able to answer any of those. So before you actually head out into the field, there's a couple critical steps that you should do before diving into the mud. And the first is getting permits and approvals to actually go out and do the sampling. You want to approach the landholders or the land managers of where you'll be doing the sampling to ensure you have permission and the proper permits to go out and collect soil cores or take some measurements of mangrove trees. You also want to undertake a work safety assessment that identifies any risk that you might encounter while you're out in the field and implements any safety mechanisms that help to minimize those risks. So another step you'll want to do before going out into the field is determining what your sample design will look like. And this will be influenced by the type of ecosystem and the zonation within that ecosystem. So let's say, for example, here on the slide, we have a mangrove ecosystem that you're going to go out and sample. And just from looking at remote sensing imagery, we can tell that there's a couple different zones within that ecosystem that have different species. And when you're sampling, you want to make sure that you get a good coverage of the species that occupy this ecosystem. So you'd want to then set up some transects that go across the different zones so that you can then set up plots within each of the different zones so that you're ensuring you get that good coverage of the different species that are present within the ecosystem that you're sampling. So as Maria mentioned in the previous presentation, there are two different carbon pools. The first is the plant carbon pool and the second is the soil carbon pool. And you want to take measurements from both of these different carbon pools, because there's 30% of carbon is stored in the plant biomass and then 70% stored in the soil. So you want to make sure that you get measurements from each different type of the carbon pools. And I'll be taking us through how to collect the data and samples from each of these two pools. So the first type of measurement we're going to focus on collecting is the above ground plant carbon pool. And the largest above ground plant carbon pool comes from actually the live trees. And so in order to measure and get an estimate of the live tree biomass that's present within the ecosystem, you'll first set up a plot, and typically we'll use 5 meter by 5 meter plots, but this can vary depending on the amount of trees present within the plot. So if you have a very dense plot, you could shrink it down, but if there's sparse and few trees, you can make it bigger, a 10 by 10 meter plot. Once you have that set up, you'll have to bring a few simple equipment with you, and that includes a tape measure, some calipers, a notebook to record your data, and if you're going to be taking tree height measurements, a laser finder is probably the easiest way to estimate tree height. So once you're in your plot, for each tree present within that, you're going to have to take and record the species ID for each individual tree. You'll also have to record, and this is the main measurement, the main stem diameter at breast height, DBH. And this is done from the ground about DBH is 1.3 meters above the ground. And as you can see here on the slide, there's a figure which is taken from the Blue Carbon Manual that shows on different tree shapes and species where you'd measure this DBH from. There's some allometric equations, which I'll talk about shortly, that require tree height. If you're using one that does require tree height, we recommend using a laser finder to estimate the tree height and record that if it's needed. If your allometric equation doesn't require that, you don't have to worry about taking that measurement. And then, to estimate the biomass, which then you can estimate the amount of carbon stored within these trees, a lot of researchers use allometric equations, and these have been developed from researchers sampling trees before and give an estimate of the biomass of the trees based on the DBH measurement. Now, there is a table in the Blue Carbon Manual that goes through, that has summarized all the allometric equations for species. And in this table, it just uses a DBH measurement. They also have another table that incorporates the tree height as well. And you'll want to use allometric equations that are species specific and also region specific. There are a lot of them out there, so hopefully you could find a research paper that would have your equation, and this just prevents destructive sampling of mangrove trees in order to estimate the carbon content. So researchers are trying to develop new ways and technologies of estimating the above ground plant biomass. Some of these include drones or satellites. There's a couple papers that I've listed here that talk about some examples in mangrove habitats. Unfortunately, while these methods are good for estimating canopy height and tree height, as I previously mentioned, those parameters aren't the main one that you need to, and is not the best predictor of tree biomass. That is the diameter of the tree stem at the DBH. So technology still needs to come along in order to better estimate tree biomass, but hopefully, new technologies will come along that will make it a lot faster and easier instead of having to go out and manually measure each tree in order to get an estimate. So another source of carbon in above ground plant biomass is actually dead trees as well. And to estimate the amount of carbon and biomass of the dead trees, you'll want to record the decay status of the dead trees. And here is another image of the varying states of decay that you would then record for each of the trees. You would also get their DBH as well, if it's decay status 1 and decay status 2, because that's you'll then use the equation calculated for a live tree, but subtract a portion of the biomass depending on the decay status. However, if it's a really dead tree, not a lot of branches, decay status 3, you'll then just measure the volume of the trunk of the tree and use that equation to determine the biomass for that status. Another source of carbon from mangrove trees come from pneumatophores. Unfortunately, the allometric equations that we would use for the live tree biomass don't account for pneumatophores, so they have to be calculated separately to those. So typically what happens is in your large plot, because there's so many pneumatophores, it would be pretty much impossible to count them in your large 5 by 5 meter plot. So typically you take a subplot, and that can be 50 centimeters by 50 centimeters or 25 centimeters by 25 centimeters, and count all of them, all the pneumatophores that are within that plot. There are some allometric equations that you can use to then just estimate, use a count and estimate the amount of biomass from the pneumatophores. If not, some people do tend to cut them within the plot, dry them, and get that dry mass that then you can convert to the biomass, and then use a carbon conversion factor, which is 0.39 to get the carbon content within the pneumatophores. But I would recommend trying to find an allometric equation for your species before doing a destructive sampling. And finally, the last main source of plant carbon that we'll go over is root biomass. Now, root biomass is very hard to directly measure. It would take an enormous amount of resources and time to go out and actually dig up all the roots in order to measure that, and it'd be very destructive sampling. And because of that in the first place, there aren't actually many allometric equations that allow you to estimate root biomass for specific species. So what researchers have recommended is that in order to calculate the below ground tree biomass, you actually use the wood density of the tree and multiply that by the tree diameter at breast height, DBH. And then once you get that below ground tree biomass, to get the carbon content, you multiply that by the carbon conversion factor of 0.39. So yeah, many people don't actually directly measure this and just use a calculation because of the enormous amount of effort it would take. So once you've measured and collected all the data for the different above ground plant carbon pools, you'll then want to estimate the total plant carbon stock. And that involves essentially summing together all the different components within all the vegetative components within the single plot. So let's say here you'll sum the live tree, the dead tree, the pneumatophores, and the roots together to get that average value for that plot. And you'll do that for each of the plots within your site. And then if you have different zonation areas that you were measuring and have multiple plots in there, then you will get an average value so that you can get a standard deviation of that. And once you have those average values within each of the different zones, you'll then, to get a total ecosystem value, then sum all of those together to get the total amount of carbon in the ecosystem. So moving on to the soil carbon pool, in order to estimate the amount of carbon stock that's stored in the soil pool, you'll have to take some cores. And taking a core allows you to get some bulk density measurements, carbon content analysis, and sometimes people will take the cores to age date them in order to estimate the carbon sequestration rate of that ecosystem. Now, these measurements require the extraction of a relatively undisturbed soil sample that's undergone minimal compaction. So that means that you'll have to use a soil coring device that works best for the ecosystem type that you're sampling in and the soil type. And there's a range of different coring devices that exist. Some include a Russian peat core. We use a PVC pipe a lot because that's easily available, cheap, and easy to manufacture. There's also augers in the video here. This is a piston auger that then allows you to extrude it and take samples right away. You also want to take cores on average down to 1 meter, but it's also very dependent on the ecosystem that you're in. Sometimes you'll encounter bedrock less than 1 meter, or other times when sampling in mangroves, people have been able to sample down to 6 meters. So it's just dependent on the ecosystem that you're sampling in and the soil, the amount of organic matter that's been stored there before. So you'll just want to get an idea of the ecosystem soil type that you're sampling in to better prepare for taking soil cores. So as I mentioned in the previous slide, when you're taking cores, you can get compaction. And this is just caused by the pressure from when you're hammering it in is causing the sediment to compress. Now, if you get something like this kind of compression, which is known as a nail effect, that maybe a root has gone across and essentially has compressed the entire core, you'll want to throw that out. That won't help you with your carbon stock assessment. And you'll want to just take a core in a slightly different area. As much as you'd like to avoid getting compaction, it can happen. As long as it's less than the core shortening that happens is less than 30%, you can still use that core, but just apply a compaction factor. And to determine this compaction factor for the core, you'll measure the height, the length of which you've hammered in the core, and you'll divide that by the actual length of the core that was collected. And that gives you a compaction factor that then you can apply to the carbon stock assessment that will minimize the skew of the carbon stock that could be caused by compaction. So once you've extracted the core from the ground, the next step, which can be done in the laboratory or depending on if you have a coring device that allows it, can be done in the field as well. And you'll need to extrude the core from whatever coring device that you are. In this video, we collected them using PVC pipes. And so we have an extruder that pushes it out that then allows us to section the core up into segments that we analyze. And so you want to decide on what your sampling depths are. So here, if you'd have a mangrove, if you're sampling from a mangrove ecosystem, because the carbon content doesn't change that quickly with depth, you can do a highly aggregated depth sampling slicing that's shown here, Whereas if you were sampling seagrasses or salt marshes, a lot of the carbon content can change drastically in the top 20 to 50 centimeters. So typically researchers do highly segmented, a lot of sampling within that depth profile, and then just larger ones, deeper in the core. So now that you've sliced up your core into the required depth intervals, in the lab, you'll do an analysis to determine two key parameters needed for soil carbon density, and that's a soil dry bulk density, and then an analysis for the organic carbon content. So to determine dry bulk density, it's pretty easy. The equation for it is the mass of the dry sample divided by the original volume sampled. So typically we get the volume by measuring the internal diameter of the coring device and then multiplying that by the length of the sample slice. So if we had a 5 centimeter PVC pipe, we take that 5 centimeters and multiply it by the length. So if we cut it 1 centimeter, we'd multiply it by 1 to get the volume. Dry mass is also pretty easy to get. You'll need an oven in order to dry your samples. So you'll want to put your sample into a pre-weighed container and put it in the oven to dry. Leave it for 24 hours, pull it out, allow it to cool for about an hour in a desiccator. And then once it's cooled, weigh it on the scale and then put it back in the oven. And then 24 hours later, come back, again, follow that same process. And if the weights are the same, I would say do it one more time, another 24 hours, and if the weight's still the same, then you can record that weight, and that is your dry mass. Now, there are two methods that you can use to estimate organic carbon content. And here is a decision tree that is from the Blue Carbon Manual that you can use to decide which method you would like to use. And the two methods include elemental analysis or loss on ignition, LOI. And I'll go through the details of both here. So up first, I'll discuss the elemental analyzer. Now, this is the most suitable method for the carbon analysis, and this is because it directly measures the percent carbon in your sample. However, it is an expensive piece of equipment and requires a lot of upkeep, so it's not available to a lot of laboratories. You could find a laboratory where you send samples to analyze them using a CN elemental analyzer. But if you do go that way, the first step is to grind up your dry sample, and this can be done manually, or if you have an automatic sample grinder, then you can put it in there as well. And in our lab, we do have an automatic one that we can put in. And so once you have your ground up sample, then another step, if you're sampling in coastal environments like mangroves, there is a chance that it could have inorganic carbon. And so you want to correct for inorganic carbon because that could contribute to the carbon present in the sample. So you want to remove it. And a way to test for this is doing a champagne test, we call it. And it's by adding a little bit of acid to your sample, to a subsample of your sample. And if you get a reaction, lots of bubbling, that means that there is inorganic carbon present and you'll need to remove that. And that's just done by adding some more acid that then reacts with all the inorganic carbon and releases it as gas. You'll then need to dry out that sample before you can prepare it for CN analysis on the elemental analyzer. And so once you've dried out your sample, you then put it into these little capsules, about 10 milligrams. And luckily, a lot of these CN analyzers have an automatic dispenser, so you can line up about 30 of them, and that they then automatically dispense and drop it down into a furnace that combusts it, and then it's analyzed in the machine, and you get a direct measure of the percent carbon. So another way to measure organic carbon content is through loss on ignition, or also known as LOI. And in the Seychelles there are, I believe, 2 labs that have the capacity for LOI. And this is because you just require a scale and a muffle furnace that can reach high enough temperatures if you're doing one burn, 450 degrees. But if your sample does have inorganic carbon, you'll also want to remove this. And this is done through a double burn at a higher temperature that removes the inorganic carbon at the higher temperature. And essentially, LOI is a measure of the mass of the sample lost when it's heated to the high temperatures. Now, the tricky thing with LOI is that it doesn't actually measure percent organic carbon. It measures percent organic matter. And there's not a clear direct relationship between organic matter and organic carbon. And so you'll need to construct an equation that relates the organic matter, your percent LOI, to the organic carbon content. This can be achieved through 2 ways. One, by sending out a subsample of all of your samples to a lab that can do CN analysis, so that then you can directly develop this equation for your specific samples. If that's not an option, then you could look in the literature for similar study locations or ecosystem type that might already have an equation developed that then you could use for your samples. So the final step to calculate the total soil carbon stock at your site is you want to then calculate the soil carbon density, and that's using the dry bulk density, which you've measured, and the percent organic carbon value that you've also measured as well. And once you got your soil carbon density, you'll then use that to determine the amount of carbon in the core section. So when you've sliced up your core into the various sections, you need to calculate it for each of those sections. And you take your soil carbon density and you multiply that by the thickness interval of that section. And then once you have the carbon in each of the core sections, you then sum that across the depth of the core that you took to get your total sampling depth. And then once you've have that carbon over your core, you'll want to take those units and convert it to a common carbon stock assessment unit, which can be tons per carbon per hectare. And once you've done that, then you want to estimate it, the total carbon stock in the ecosystem that you've had by taking your average carbon value and multiplying that by the area of your ecosystem. And then once you have those values, you can then translate that data into blue carbon assessments. And I'm going to hand it over to Dr. Michele Costa from the Blue Carbon Lab, and she has undertaken several of these blue carbon assessments using the data that we've collected in the field, and she'll walk you through the next steps.
Hello, everyone. So now I'm going to talk to you about how you can translate this data collected from the field into blue carbon assessments. And basically how you do it is going to depend on your carbon data availability and the main objective of your study. So thinking about the availability of carbon information, we usually have 3 main situations. So the first one is where we are in a very data poor region that we don't know nothing about carbon in this area, and we ended up needing to use some IPCC default values, which are basically some global averages for carbon stocks for each specific blue carbon ecosystem, like meaning mangroves, seagrasses, or salt marshes if you are in a region that has salt marsh. Then we have a situation where our country or our site is specific. We start to get this data at the area of interest that we have. And this increases the accuracy of our assessment. And the last one is where we go in a very detailed carbon inventory with repeated measurements through time. So basically, imagine like you going back to these sampling locations in different times of the different years, and you just create these large and highly specific carbon data for your site. And then after this, like evaluating where you stand on the carbon availability for your area of interest, you need to think, okay, where do I know where these ecosystems are? Or so, for example, if my area of interest is just like a project site, or if I'm talking about like the entire country, I really need to understand where, which blue carbon ecosystems I have and where they are, or how much area they actually occupy in my area of interest. And for that, we can use existing distribution maps, or if we don't have these existing distribution maps, or if we have and they are not that, they don't represent our area accurately very well, we can actually go and use remote sensing techniques to actually help us map these ecosystems for our area of interest. Thinking about remote sensing itself, especially for mangroves, because they are easier to map and to see from the space. There are a few studies that have also used sensors to estimate and predict mangrove above ground biomass and carbon stocks based on remote sensing techniques. So if you're working in mangroves, definitely worth to have a look in these studies. But basically, what we need to know is, okay, how much area our ecosystems occupy and how much carbon per unit area we have. And we can easily then combine these two information to have like our carbon assessment for this specific area of interest. Some other examples, and it goes towards more like complex modeling, is when we use statistical modeling to predict carbon at a greater distribution extent. So here, for example, is a study that we conducted last year in the Great Barrier Reef catchments in Australia, where we had several sampling points where we collected carbon data for mangroves and salt marshes, like throughout our area of interest, which is shown in that map. And we combined this information with environmental variables that we knew to influence carbon stocks for these two particular ecosystems in this part of the world. And we used statistical modeling to actually understand the relationship between these two information, and then use these relationships to actually predict throughout the ecosystem extent how much carbon we would have in a specific resolution. So these are different from the previous slide, where you just get like a final value in based on the area that your ecosystem occupy. Here we have very like a spatially explicit information of carbon stocks in each different pixel. So this is also another thing that you could use your data from the field for. But in this case, you really need to think about that, especially if your area is like a larger area, you really need to evaluate if your carbon information actually is well distributed throughout your area of interest. So you need to have like a really good representation of carbon in different ecosystems, or if you are interested in only one ecosystem. Yeah, so you really need to plan and design your study really well, thinking about the environmental variables you're going to use and the representativeness of your carbon data within your area of interest. And there are other things to consider as well, such as, for example, which statistical modeling to use. I'm not going to get into much detail here because it's also not the purpose. But there are heaps of studies that use it, like similar approaches for these. And so please let me know in your questions if you're interested on these, or don't hesitate to email me, and I can definitely share some other examples with you. And there is another example that we can use our data from the field for, which is basically if you're interested in understanding how changes in land cover could actually change your carbon sequestration through time. So in this case here, also an example from the Great Barrier Reef catchments in a work that we conducted late last year, early this year, where we were trying to identify areas that would be amenable for blue carbon restoration. And we were interested to understand how much carbon we could potentially store and sequester if these ecosystems were restored. So the model that we used here was the Coastal Blue Carbon model, which is part of the Natural Capital Invest modeling package. So definitely something to have a look as well if you're more interested in understanding how carbon can change through changes in land cover. So I hope you enjoyed this section, and please don't hesitate to make any questions or reach out by email if you want to discuss any of these topics in more detail. Thank you.
All right, thank you, Maria, Mel, and Michele for those insightful presentations. In the essence of time, perhaps we can take 2 questions, either from the online participants or within the room here, before moving on to session 2. Just bearing in mind that we do have 10 minutes allocated at the end to ask more questions. So perhaps we can take 2 questions now, if anyone has any. Yes, we have one question. Please introduce yourself as well as the organization that you're from. Thank you.
Thank you, and thank you for the presentations. They were really interesting and learned quite a few new things. My name is Helena. I work on the Marine Spatial Plan Initiative. And my question really, sorry if I've missed it, but I was wondering, how do you calculate the blue carbon content of, say, a particular area through the core sampling without knowing, for example, the depth profiles? So how do you do that? You know, like in the beginning, there was some limitation on how far you can take the core. So I was just wondering how you would factor that in when you do the estimate. Thanks.
So just to clarify the question, you're wondering how to factor in the depth?
Yes.
In your carbon. So essentially, you're summing the carbon content across the entire length of the core that you've taken, and then you can then have it down to that depth, and then you'll multiply that average carbon value to, say you took a 1 meter core, you'll multiply that by the area of the ecosystem that you're sampling to get that total area carbon stock, and then you report that down to 1 meter because that's the length of the core that you took. But if you just took it to 50 centimeters, you'd just be recording it down to that depth, if that makes sense.
Can I just follow up? Sorry. I was just wondering because, you know, the Seychelles Islands are granitic, And I'm just wondering if you'd be able to get a 1 meter core across an entire area that you're sampling. That's why I was asking that question. Yeah, so it's just an assumption, right?
You should definitely ask Barry about this when you're out in the field, because he's been doing all of our sampling on the island, and I believe they've been able to get some down deeper, around 80 centimeters, but others have been shorter. Barry, maybe you can comment if you've been able to read the meter.
Yeah, there's been a few. Thank you. There's been a few occasions where we managed to get down to 1 meter, and but the majority of the sample reached down to about 70, 80 centimeter, which for us in the ecosystem that we are working with is it's quite good. And we were told in some, for example, in Adaptation, we will not be able to get down to 15, 20 centimeter, but the average on Adaptation is 60 centimeter managed to get to. We'll show you a little bit later on the equipment we're using to get to that depth. So we had to invent an auger to get to that depth. Thank you.
Thank you, Barry, and thank you, Helena, for that question. Maybe we can take one more question, if anyone has a question online as well. There doesn't seem to be anyone in-house. Okay, should we move on to session 2?
Hey everyone, so I'm Dr. Michele Costa, and I'm a research fellow here at the Blue Carbon Lab at Deakin University. And I'm going to talk to you about blue carbon in Seychelles. So as part of this project, we conducted a very thorough literature review in blue carbon studies conducted in the Western Indian Ocean region, including Seychelles. And what we found is that potentially blue carbon ecosystems in Seychelles could be storing around 116 tons per hectare in seagrass soils and 3 tons per hectare in seagrass biomass. And for mangroves, we would have around 109 tons per hectare in plant biomass and 369 tons per hectare in their soils. So these values are based on the literature and previous studies in the region. And we're really looking forward to updating these numbers based on the field work that has been conducted as part of these 2 major projects happening in the country, led by FEW, in the case of seagrass meadows, and led by us in the case of mangrove forests. So stay tuned in regards to the outcomes of these 2 projects if you're interested in blue carbon ecosystems. So based on that, and the fact that we know that Seychelles has around 2.1 million hectares of mapped blue carbon ecosystems, from which 99% is actually seagrass, we can easily estimate that seagrass meadows in Seychelles would potentially store around 250 million tons of carbon throughout their entire distribution, while mangroves, which has like a more restricted distribution in the country, would potentially store around 111,000 tons of carbon in the country. Overall, these ecosystems would hold just over 250 million tons of organic carbon, which is equivalent to 920 million tons of CO2 equivalent. Personally, I like to think about blue carbon as a great opportunity, but also as a great responsibility. Because if these ecosystems were lost, let's say, for example, due to coastal development, this carbon that has been stored for years, centuries, and millennia in their soils can actually be released back to the atmosphere. And in the case of Seychelles, if we put that in perspective, that could be an equivalent to the annual emissions of 200 million passenger cars. Moving forward, also as part of this project, we conducted a stakeholder survey where we distributed a questionnaire to more than 200 stakeholders that work closely to blue carbon ecosystems in Seychelles. And our main objective was trying to understand the local knowledge on social, political, ecological, and scientific context of blue carbon ecosystems in the country. And what we found is that most stakeholders actually work in the government, and that people have different attitudes towards coastal ecosystems. So, for example, people tend to be more positive to mangrove, probably because of we have better education and awareness programs in the country. In contracts for seagrass, people tend to be more indifferent or slightly negative. So this type of information is really important to guide future projects in the country and how to create better connection between communities and blue carbon ecosystems moving forward. Despite seagrass being widely distributed throughout the country, mangroves are more studied than seagrass, with research mainly focused on plant taxonomy and mapping, with only little attention to the potential of carbon storage. We also asked what would be the main limitations of blue carbon research in the country, and 90% of respondents actually mentioned the lack of funding, lack of facilities, and lack of equipment. Again, really important information to help Seychelles foster blue carbon in the country, just kind of like having in mind where they need to invest to enable future research. We also tried to understand the scope for protection and restoration in Seychelles. Respondents mentioned that up to 45% of coastal wetlands are protected, but regardless that, up to 60% of coastal wetlands are still being degraded, with coastal development being cited as the top environmental threat to blue carbon ecosystems. This is really really interesting information that can actually help us understand and guide future actions towards restoration, and not only restoring ecosystems where they have been lost, but also trying to restore areas of these ecosystems that might be in poor condition. We also asked about environmental concerns and the top co-benefits provided by coastal wetlands. The top environmental concerns cited were extreme events, inundation due to sea level rise, and other impacts due to climate change, which were actually matching the top co-benefits provided by these ecosystems, with coastal protection being the first one, followed by coastal sequestration and fisheries enhancement. We also trying to understand if the respondents knew about the relationship about these ecosystems and coastal revenues. And what we found is that most of the respondents are expected these ecosystems to provide relatively similar profits, and in this case profits would be from fisheries enhancement rather than tourism itself. And I think just to finalize this section, I would like to bring to your attention the Seychelles Blue Carbon Roadmap that we are developing as part of this project, and we expect to deliver by the end of this month to SeyCCAT. And this document will set a long-term pathway for the country to establish an 8-wild program towards blue carbon ecosystems. And as part of this document, we have 4 main areas: research, community, governance, and financing, where we set a list of objectives and actions that should be taken in the next few years to enable blue carbon research in Seychelles. So in research, for example, the main objective is to deliver research to quantify blue carbon eco-benefits, and the actions would be from building local capacity, enabling sharing of research data and knowledge, develop a nationwide heat map of blue carbon stocks, sequestration rates and changes in distribution extent, and also improve the evaluation of co-benefits for inclusion in blue carbon project assessments. In community, the main action would be to connect communities to blue carbon ecosystems through exploring community acceptability of blue carbon, stressing blue carbon education and awareness, and enable communities to participate in blue carbon stewardship projects. In governance, the main action would be to integrate blue carbon into national policy frameworks through optimizing governance and legislation of blue carbon in the country, clarify legislation around crediting rights and ownership, which is going to be really important if we Seychelles go towards the finance pathway, and also advance the blue carbon commitments included in the revised NDCs. And finally, in financing, the main objective would be to connect blue carbon ecosystems to carbon markets and other finance mechanisms through their restoration and conservation. And for that, the main actions would be to explore and test effective mechanisms for financing blue carbon projects, develop costal and benefit analysis of restoration strategies, and also to implement some blue carbon demonstration projects. So I think that's it for this section. I'm looking forward to get any questions that you may have, but also if you want to discuss any topic in a specific in more details, don't hesitate to contact me.
Thank you, Armia. Thank you for the SeyCCAT team for inviting me to this workshop to show you a little bit of the work that we are doing in the field. We will have our workshop sometime later during the year where we can give more detail about the work that has been going on. But for the sake of this workshop, we've decided to talk a little bit about how we go about in the field and doing the work. Most of the things I want to talk about this morning, Mel has already covered them in terms of the procedures and manual that we're using and the steps that we take going to the field. So I'm not going to go into all that. So what I'm going to do, can you just help me out with the... go through. First of all, the first thing you need to bear in mind when you get into the field is, what am I getting into? First of all, mangrove ecosystem is nothing like the normal place you walk, your street, everywhere you go, in your hike on your trail. It's nothing like that. One of my the staff that is working with me calls it l'endroit normal. Normal. When she's outside of the mangroves, she's on normal ground. When she's in the mangrove, it's not normal ground. So we come to describe it like that. It's a very difficult ecosystem to walk in. First of all, it's muddy. If you are walking in places like Adaptation, the coral is not your good friend. It will tear you apart. We've had a few injuries. You need to know what you're getting into. You need to know what kind of ecosystem you walk into so you can make sure that you have the level of safety that is required that goes with the work. That's number one. Number two, you must make sure that you have the right equipment. One of the challenges we had when we were going to Adaptation, and Mel will remember that, was to decide how we're going to get all the core from Adaptation to Mahe. Originally, the idea was to take cores using PVC, but you're going on Adaptation and you're going on in a place where you have hard coral, and you need to get through some of these coral layer, which is quite challenging. So PVC is not the ideal equipment to work with. So we had to decide how do we go about doing that. So I have a friend of mine who is a bit of a freak. We're working with metals and stuff. So we decided to use a model that we received from Deakin, from Mel, more precisely, where we were advised to use perforated PVC, where we can take every 10 centimeter interval to have a distinct access for us to take the core out. But the PVC didn't work, so we had to use another material, and then that's when we went for using stainless steel tube, and stainless steel we had to use marine grade. I was just talking about the ecosystem, we managed to get it working? Okay, thank you very much. So we can keep it right there, just to give an idea. So this is what we meant. We need to have a little bit of understanding, the species we could expect. So we need to learn the species, we need to understand, to look at the features and understand and know what species exist. So these are a few species that we've encountered on our journey so far, and we are yet to get another 3 in our collection. So the next slide. The gears that we have to make sure we need to have. Safety clothing is very important. You cannot wear boots. We've tried it in our mangrove ecosystem. I don't know about other places. Boots, the normal boots, gum boots, is useless. The minute you step into the mangrove, it's gone. Okay. So the best to use is the booty. We call that. Ami would know the name better than me. What do you call it? Water boots. Okay. I'm a soil scientist. He's a marine biologist. So safety, like I just mentioned before, we need to have some first aid kits. You need to have that with you. You can't go back or leave any wound open. You need to find ways to make sure that if any injury happens, you must have a way to contain it. This is the gadget I was talking about earlier. This is the stainless steel core that we designed based on the PVC model that we were provided. And this actually works very well because it allows us to take the core, the full length of the core, which we can have the full measurement of the core, like and the question was raised earlier. So once we measure it with the full length of the core, we can also, it's hollow, so you can take the compaction in and also take the compaction outside. And also we can access the sample while it's still in the tube and take it out using a 40 millimeter PVC, small PVC tube, and that will pack it and then we can transport it. So instead of having the whole length of tube taken to the lab, we do the slicing using that little core that we take to the lab, which allows us to carry about 60 to 70 grams of sample into the lab, which is representative of the various depth. Next slide. Field selection. The field was pre-selected by the team who was working on the project earlier. So on Mahe, in Ireland and out Ireland, there are 17 locations. By far, I think we've covered about 12 or 13 locations. So we're not far of our target. Like Mel mentioned, the plot size is subjected to the density of the seedling or the mangrove that's growing in the area. So the density decide what size of plot you're gonna select. You can't select a 5x5 area when it's a lot of seedling. It's gonna be quite cumbersome for you to do the counting. And we've been advised to make sure we take the sample from seaward to landward. But as you know, in the case of many of our mangrove area in the country, you don't have that seaward, landward as a straight line most of the time. So sometimes you just run along the coast and you need to make certain decisions in the field. So there are certain decisions you need to make, and it has to happen because that's the way the ecosystem is. And the number of transect, like it says here, it will vary. It depends on the size of the mangrove forest. So you can go for a transect of 100 meters, and in some cases you have to go for 50 meters transect. It all depends on the size of the mangrove forest you're working with. Yes, that's fine. So that's a little bit of the measurement that we do. The plant height, which is a requirement on our side. We have mangroves that are above 12, 15 meters. So how do we get up there? There was a suggestion earlier, Mel said we can use the laser finder. Sometimes that doesn't work as well, because how do you get to all the leaf to get to the top one? So we came up with an idea is to use total station. Total station is what they use in survey. So it's the equipment you can see here in the second picture, the yellow equipment. You will see that in the field how it works. What this does, it can take the measurement from away from the plant. You can stand on the road wherever it's possible for you to see the plant, and you can take the measurement from the very top. And then my friend there will explain a little bit how this operates. So, and also you need to know from the ground what is the actual height. So that equipment also allows you to do that. Another information that is important is the location, the elevation at the location. You need to know what elevation you're working at and at the specific location. Sometimes you get trouble using GPS to do that. The ideal way is to use the GPS, but it doesn't really work. So the total station allows us to overcome all those challenges in the field. One of the challenges with the total station is that it's a bit bulky, so you need to be able to carry it in the field. We had this discussion, and I barely remember. And one of the questions was like, how are you guys going to carry the total station around Aldabra? We did that. So we made it work. We made it work. So that helps a lot. Next slide, thank you. A little bit of the mapping that is ongoing right now. We're producing 3D imagery of the various places we are going. So we're producing quite a bit of map, which can be used later on by Deakin in their process of analysis. And also this will help us in situation where we can absolutely not get any access to measure the height of the plant. So that's another way of getting to it, because at the same time, Hendrik at the back can explain also a little bit how this works. So these are all the above ground work that we do. I'm not going to go through this one. Mel already covered it, so I can skip this one. Just to show you a little bit of how this is done, Mel already explained the compaction in, compaction out. That is very important because, as Mel explained, we're going to do the bulk density. If your sample is compacted beyond 30 centimeter, or beyond 30%, sorry, it gives you a false indication of how bulky your soil is. And when you make an interpretation on the amount of organic matter on a dry wood basis, and that will offset your result to some extent, and you don't want that to happen. So the best is to limit yourself to make sure that you have minimum compaction possible, if possible, zero compaction, which is quite difficult, but we get very close. Thank you. Lab work. Before we get to the lab work, we need to preserve the soil. As you all know, soil organic carbon, like Mel rightly pointed out, soil organic carbon and soil organic matter are two different things. Soil organic carbon can be influenced by microbial activity, and that will potentially affect your result. So what we decided to do is that the sample has to be kept at temperature 0 degrees. So we've got the assistance of a colleague of ours that is helping us with cold room facilities. Make sure that the sample are kept at the temperature that is to prevent any microbial activity that can actually affect the organic carbon in the soil. The bulk density, again, we've managed to produce sample ring, standard sample ring that allows us to have the volume being maintained, the volume of the sample being maintained, so that we can have all the sample with accurate volume measurement by using those little sample ring. My picture is not that big enough, so sorry about that. So the sample ring allows us to measure the bulk density directly without having to using what we call the sausage, having the sample removed and then trying to compact it all together, but the ring allows us to do that much easily. We are currently in the process of processing the sample for bulk density, so a couple of samples are being analyzed, and one of our colleagues is actually in the lab right now continuing the analysis. Miss Natalie Mahe is doing that for us, and thank you to the Ministry of Agriculture, Environment and Agriculture for allowing us to use the facilities for this analysis. And lastly, I'm sure you're not going to be able to see that, but we're using Excel as the main tool right now for us to compile our data. So every single piece of data that Mel has spoken about is actually in this template. That template was produced for us and submitted to us by Deakin Blue Carbon Lab, and we are in the process. We are more, I would say, about 80% completed with this data set. And Ms. Fatima at the back is one of the one person helping with the data compilation. So let me just go now briefly introduce the team that is working on this project. I have myself, Barry Norris, Dr. Ami Ibrahim as consultant. I have Mr. Hendrik Yupa, who is assisting us as an expert surveyor and drone expert. Ms. Jill Esparon and Ms. Fatima, who have worked in the past with Ms. Elvina Ayed on several mangrove forests, so we have already already have the background in the measurement and taking sample in mangrove. And I have also Mr. Jean-Pascal, you see him next to Fatima here on the far right on your screen. And he is also an assistant surveyor and helping us also with this initiative. I have in the room here Mrs. Monette Norris, who is helping us to coordinate all our activity, because you need a team. This is well coordinated. You can't do all this work without just going outside like that. You need to plan everything. So she's the one behind all the planning and organizing all the visit. I put this picture, sorry, I missed one more. Miss Alicia Bells, the UNICEF student, who is working with us on this project, and she couldn't make it for today's presentation. I put this picture here just to raise a little bit of awareness. I don't think we understand the importance of mangrove yet. We assume it helps with clearing the water, making sure with ecosystem services. We heard the former president talking about the importance of mangroves. But this is a situation on Sidwet right now, where coconut seedling is invading a beautiful mangrove forest at Anslaska. And within that mangrove area, we have a lot of seedlings of cinnamon growing. And the intention is not to deal with this right now, but to try and rehabilitate another mangrove area which is already dead because of the same problem. So we need to have plan. We need to understand the importance of this ecosystem and do our best to preserve them. So that will be a little bit of our take on this for today, and I hope we managed to explain a few things. I think the most important activity is to go out and actually try it, do some heavy lifting, and see how the whole process happens in the field. Thank you very much.
Thank you very much. I think we can now have a few questions, if anyone has any few questions, either for Barry or in general. Sorry. I think we have some. No questions from anyone online? I see we've been joined by the Aldabra team that are actually stationed on Aldabra. Welcome. For President Michel, do you have any comments or questions?
So how many of you are going in the about your booties or yes?
Okay, so if there's no questions, I would just like to thank. Sorry, we have one question from Annabelle. No problem.
Barry, I was just wondering, hi, Annabelle from SIA. With the device you use, the Alba, this is ingenious, like really, congratulations. I was wondering if you had any issues with like waterlogged conditions, because there, how do you get rid of the water before you're able to pour out the cement?
Actually, we don't need to, because when you push the auger down, because of the perforated area, so the water goes out as the auger goes down.
Is there then a concern that you are actually pushing out not only water, but you have some higher organic material?
The way the auger is designed, even if you were going to put a PVC, you still have losses. But the way it's been designed, as it slides down, you pass over each layer, and once you hit your targeted layer, it's actually sealed in. So when you're pulling it out, it will not make much of a difference, because if I was going to use a gauge auger, for example, a gauge auger is completely open on one side. Okay, so the same effect, will have happened. In fact, it will have been probably more. So, but using this particular auger, this problem is quite well overcome. Yeah.
Perfect. I hope you patent this.
And I have to ask Mel where she got that first, because I might patent some ideas that is not mine.
I couldn't hear the question.
Yeah, sorry, Mel. So basically, Annabelle, that we know quite well, was asking a few questions with regards to the auger that we were using, and if there's any loss of organic carbon or any water compaction that may happen. And that's when Barry stepped in and clarified the issues there. It was also raised by Annabelle that we should probably patent this auger, so we probably have to go through you.
No, I mean, that design's been used before. Typically, it's a PVC pipe that they've drilled holes into, but very, was smart and made it metal. So having that sharper edge helps cut through the organic matter to help lessen compaction. So definitely Barry's choice of metal was very useful in the design process. So well done, Barry.
Thank you. Well, I shall have to say thank you to Jean-Paul, who's not here in the room as well. But one of the reasons why we decided to go with stainless steel is when we use the PVC, one thing we notice is that when the tube is going down, because PVC tend to have some sort of friction, so that increases the tendency for the soil to compact. But the same area where we've used the stainless steel tube, we've seen quite much less compaction, because PVC cuts through and it's slippery. Only when you hit the bottom layer where your soil tends to lock in. So you avoid all this problem of compaction overall. So it helps quite a lot. And also working with PVC, you don't have any, you have minimum contamination. If you were going to use the sample later on for further analysis, a lot of the PVC that you use, that we get here, are construction grade PVC. They are not PVC that is designed for scientific work, and you can carry contamination into your sample. But the PVC we're using is the marine grade PVC, and if you can use the sample for other work later on, which will not have any contamination. Okay.
All right, thank you very much. Again, I would just like to thank everyone in attendance online. I would like to thank you, the Deakin team, Maria, Michele, Professor McGreedy, and Mel. Thank you so much. It was really insightful hearing about all the techniques and all the hard work that we put into this project. So now I think we off to the fun part of the session. We'll send you guys lots of photos. But before that, everyone, there's tea and coffee and snacks outside, so please help yourselves. And we've also been given access to the gym area lockers, so if anyone needs to change, that's also available for us to use. I'm pretty sure they fill yourself and directors accordingly. So thank you very much, everyone. And thanks again, Deakin team. We'll keep you guys updated.
Thank you.